Could there be a vast quantum computer in the universe? If given a quantum twist, computational rules might be able to represent the evolution of the cosmos better than the dynamical equations of physics. Except for a charred obituary in the New York Times, the death of US computer scientist and physicist Edward Fredkin in June went mostly undetected. But even though Fredkin never quite achieved the level of notoriety that some of his contemporaries did, he nevertheless had a significant impact on both of the fields he crossed. His main argument that the laws of physics, and even those of the universe itself, are fundamentally the output of a computer algorithm, remained unpopular with many. However, the digital physics that Fredkin promoted has evolved from being out of the ordinary to becoming practically conventional. Fredkin was in charge of Project Mac, a research facility that became the MIT Laboratory for Computing Science. The role was only one in a large portfolio. He did a lot of things in the real world, said Margolis, who is now a freelance researcher connected to MIT. Innovative thinking. AI was still mostly a theoretical idea in the late 1960s, but Fredkin was ahead of his time in recognizing the dangers that learning and autonomous decision-making computers face for national security. He promoted international cooperation in AI research because he understood that reaching an early agreement on how the technology should be applied would prevent issues in the future. An international gathering of the leading minds in the subject was attempted, but it was unsuccessful and remains a failure to this day. After leaving MIT in 1974, Fredkin spent a year as a distinguished scholar at Caltech, where he made friends with the physicists Stephen Hawking and Richard Feynman. Later, he took a second job at Boston University after accepting a tenure-track professor position at Pittsburgh, Pennsylvania's Carnegie Mellon University. From that point on, he began working on reversible computing. Reversible computing was then commonly believed to be impossible. A typical digital computer is built from a series of logic gates such as ANDs, ORs, and CORs, and others, where two inputs typically result in one output. Heat is produced while the supplied data is deleted. Together with Margolis and a young electrical engineer from Italy named Thomas Satofoli, Fredkin demonstrated how certain gates with three inputs and three outputs, which came to be known as Fredkin and Toffel gates, could be configured to preserve all the intermediate steps of any conceivable computation, enabling the process to be reversed upon completion. A computer constructed with those gates may, theoretically at least, emit no waste heat and so use no energy, as they proposed in a seminal 1982 paper 1. At first, this didn't seem like much more than an oddity. Fredkin believed the notion could contribute to the creation of more energy-efficient computers with less heat waste, but there was no practical method to implement the concept entirely using conventional computers. But when Fredkin and Toffoli organized the Physics and Computation Symposium at mid-1981, the course of history was changed forever. Among the luminaries in attendance was Feynman. In a now famous contribution, he proposed that some physical systems that exhibit quantum behavior would be better tools than trying to imitate quantum processes with ordinary digital computers. Small quantum computers are now being developed after 40 years. Electronic physics. Fredkin and Toffoli started working on reversible computation in a somewhat different way in their 1982 publication. It began with a seemingly silly comparison, a pool table. They demonstrated how fully reversible billiard ball interactions, assuming a frictionless table and frictionless ball-to-ball exchanges, might reflect mathematical computations. Toffoli's hypothesis that computational concepts would be a better method to capture physics than the differential equations typically employed to explain motion in change gave rise to this physical manifestation of the reversible concept. Fredkin went even further, coming to the conclusion that the entire universe may be viewed as a type of computer. It was a cellular automation, in his opinion, a group of computing bits or cells that can change their states in accordance with a set of rules that are based on the states of the cells around them. These basic principles have the power to eventually give rise to all the intricacies of the cosmos, including life. He wasn't the first to experiment with these concepts. In his 1969 book Calculating Space, Konrad Zuse, a German civil engineer who had created one of the earliest programmable computers prior to World War II, proposed that the universe may be seen as a traditional digital cellular automation. Despite the fact that Fredkin himself first used the phrases digital physics and digital philosophy, more recent versions of the idea have instead employed labels like pancomputationalism and digitalism. Scientists who have supported them include US physicist John Wheeler, whose famous "it from bit" remark is a succinct formulation of the concept, and Dutch physicist and Nobel winner Gerard Hooft. We enter the quantum world. Margulis is one person who has continued to refine the theory's traditional form. However, when quantum rules are substituted for the classical computational rules of Fredkin's digital physics, many of these issues disappeared. In a way that a theory based on a classical concept cannot, you can capture intrinsic properties of a quantum universe, such as entanglement between two quantum states separated in space. This viewpoint was advanced by Lloyd in a number of studies beginning in the 1990s and in his 2006 book Programming the Universe. Such theories stand in stark contrast to the more contemporary hypothesis that we are part of a computer simulation, which was put forth, among others. By the Swedish philosopher Nick Bostrom at the University of Oxford in the United Kingdom. The fundamental concept of a digital universe may very well be testable. However, a quantum theory of gravity that proves the connection between quantum effects on the microscale and Einstein's general theory of relativity would likely be necessary to really nail down the concept. Theorists have yet to understand this. Take the holographic principle, which was developed by Hooft and states that our universe is a projection of a lower dimensional reality. It seems hopeful that these quantum digital universe ideas might be able to shed some light on some of these mysteries. That would be the most recent turn in an unusual tale. In his own opinion, Fredkin's lack of a conventional physics education contributed to the development of his unique points of view. Lloyd largely concurs. I believe he would have produced less interesting work if he had received a more traditional education, had he advanced through the ranks and taken the required physics courses, for example.